Hi, we are going to talk about the multiple linear regression model. It all starts when you have an economic model that you want to test. For instance, you have a model that says that wage depends or is a function of hours worked, IQ, knowledge of the work world, education, experience, tenure, and age. Now, you are going to collect a representative sample of the population to which you want to apply the model, and you are going to estimate an econometric model. And the econometric model says exactly the same, but it gives a coefficient to each of your variables and adds it a residual variable, which means that this model is probabilistic instead of deterministic. So let's go to SPSS to estimate. Analyze, regression, linear. We choose our dependent variable, wage, and our independent variables, which are hours through age, and we move them into independent variables box. Next, we go to statistics, and we click in R-squared change and in collinearity diagnostics. We press continue, and in plots we are just going to choose the histogram and the PP plot. We could choose some things more, but we will leave it to the diagnosis and tests phase. And we are not going to save the predicted values yet. So let's click OK and move to the estimated model. And here we have the SPSS output. The first table tells us what our dependent variable is, wage, and all the variables that we entered into the model, and the model accepted all the variables and removed none. Next, we have the model summary that tells us several things of interest. First, the coefficient of multiple determination, which is an analog of Pearson's correlation coefficient for the correlation between the dependent variable and the independent variables in our model. So there's a moderate correlation between all our variables, our independent variables, and the dependent variable wage. Next, the R-square, which is a measure of goodness of fit, and it is the square of the previous measure. So R squared means this R squared. And it shows the percentage of variance that our model was able to explain. The adjusted R square includes a penalty for each independent variable that we add to the model. So globally, we have a 19% variance explained, which is not exactly brilliant. So if this tells you how much variance we were able to explain, how good was our fit, this measure, the standard error of the estimate, tells us how precise our estimate is. It is in the units of the independent variable. So if we are trying to estimate wage, which is in US dollars, this value is in US dollars as well, and tells you on average how far are the residuals from the predicted values, from the fitted values. We are not going to look at these values right now, but we will come back in an ulterior phase. Now we move to the ANOVA table, where we have several informations of interest. Here we have the total sum of squares. That means the variability of the dependent variable. This is the variability that we were able to explain through our independent variables, and this is the unexplained variability associated with the residual variable. If this is the total sum of squares, this is the mean square or the average square. So this is the sum of squares of the regression divided by the degrees of freedom, the number of independent variables that we use, the constant is left out, and here we have the mean square of the residuals, which is this value divided by n minus k, which is the number of independent variables, minus 1. This F statistic is the ratio of the mean square to the mean square residual. That is, how many times the explained variance is larger than the unexplained variance. Here we have the p-value associated with an hypothesis test, the test of the global significance of the model. It has under the null hypothesis that the coefficients of our model are jointly equal to 0. And here we reject the null hypothesis, meaning that at least one of our coefficients is different from 0 in the population. Now, the information regarding the coefficients, the value of the estimated coefficients of our model. Here we have our betas, the coefficients, beta 0, beta 1, beta 2, etc., each associated to one of our independent variables. The betas are in the values of our dependent variable, so if we have dollars, each of the coefficient reads like a dollar measure, and it means, for instance, that for any additional year of education, the wage increases by $46, roughly. To the right, we have the standard error of the coefficients, which is a measure of how precise each coefficient is. Okay, the smaller the value, the better, because it means that the coefficient was estimated without much variability. Here we have the t-statistic, which is the ratio of the coefficient to its standard error. The larger in absolute value, the better, because it means smaller variability. A rule of thumb tells us that the t-statistic should be higher than 2 in absolute value. To the right of the t-statistic, we have the p-value associated with an hypothesis test, which is the hypothesis test of the individual significance of each coefficient in the population. Keep in mind that we are performing inferential statistics. We are estimating with a confidence level. We are not estimating with certainty. And on the other hand, you will not look at these coefficients if you are performing regression on a population, because in that case, you know the population with certainty and you don't need to estimate with confidence. So this p-value allows us to solve each of the hypothesis tests, which has under the null hypothesis that each coefficient equals 0 in the population. Okay, for most of them, except for hours and age, we reject the null hypothesis that the coefficient equals 0 in the population. Finally, we have a collinearity measure, in fact two, tolerance and VIF, but VIF is the inverse of the tolerance, and this tells us if we have collinearity present in one of the variables or in more than one. And collinearity is the fact that a variable is a linear function of other or some of the other variables. So tolerance is 1 minus the r squared of an additional regression, in which we run a regression of one of the independent variables on all the other independent variables. So we would like that the explaining power of each variable on each other to be as low as possible, meaning that each variable explains different phenomena. So to preserve the individual explaining power of each variable, we need high tolerance values close to 1 or low variance inflation factor values close to 1 as well, especially when we have VIFs close to 10, which means tolerance close to 0.1. We have problems, we have severe collinearity, and we will have to exclude that variable. So estimation and interpretation basically end here. We have these values. We have to check if the values of the coefficients are in accordance with the expected sign in our economic model. We have to check if they are large or small in absolute value, and we have to check if they are statistically significant, meaning if they are different from 0 in the population. We cannot keep statistically non-significant coefficients in our model, and this means that we will have to remove age and hours, and we will do that in the iteration phase, which is the next one, and we will proceed step by step, removing age first and seeing what happens to the model afterwards.